Welcome to How to Locate Black Holes, from radio waves to gamma rays. I'm Nan Janney from the National Radio Astronomy Observatory's Education and Public Outreach Department. It's Black Hole Week, and today we have a great team of panelists to discuss the way astronomers using the Very Large Array and NASA's Fermi Gamma Ray Space Telescope locate black holes. The format goes like this. Our three panelists, moderated by NRAO's Amy Oliver, will be talking about the essentials of all things black holes. The question and answer in Zoom will be open for posting your questions, and the chat on the side can be used for commentary. But remember, if you ask a question in the chat, we won't be able to get to it. If you're watching on Facebook and want to ask a question, we'll be monitoring the comments section, trying to post as many of your questions in Zoom as possible. So let me get now to our moderator, Amy Oliver. Amy has recently joined the NRAO Education and Public Outreach team as the news manager and the public information officer for ALMA Observatory. Previously, she covered the communications for numerous observatories and telescope systems, including the Event Horizon Telescope, Very Energetic Radiation Imaging Telescope Array System, South Pole Telescope, Hubble Space Telescope, Green Bank Observatory, and many more. She has worked directly in astrochemistry, theoretical physics, and computational physics. Outside of work, she is a contributing science writer to Earth Sky and is a NASA JPL Solar System Ambassador, where she creates accessible gateways to science learning and NASA missions through informal education experiences, and leads the Spanish subgroup. Welcome, Amy. How are you today?
Thanks, Nana. I'm good. I'm so happy to be here. Thanks for letting me help out.
Well, we are excited to have your expert moderation and knowledge. Where are you Zooming from today?
I'm Zooming from a place called Rio Rico, Arizona, which is about 12 to 15 minutes north of the Mexican border in southern Arizona.
Oh, wow. Okay, so you're pretty far away from our headquarters in Charlottesville. Well, I know people are excited to start the seminar, so I'm going to turn it over to you to introduce our panelists.
Great, thanks so much.
Okay.
All right, guys, so now we're going to get started with introducing our expert group of panelists, just like Nan said. First, I want to introduce you to Dr. Amy Kimball, who is a staff scientist at the National Radio Astronomy Observatory in Socorro, New Mexico, where she supports users of the Carl G. Jansky Very Large Array. Dr. Kimball is the head of operations at the VLA Sky Survey, which is in the process of imaging the entire radio sky visible to the VLA at very high resolution. She uses the VLA and other telescopes, both radio and non-radio, to study the demographics of quasars, which are supermassive black holes at the centers of large galaxies. Next, we'll be welcoming Dr. Justin Fink, who has been an astrophysicist working in the Space Science Division of the U.S. Naval Research Laboratory since 2007. Dr. Fink studies gamma ray emission from plasma jets accelerated by supermassive black holes with NASA's Fermi Gamma Ray Space Telescope. And finally, we'll also be hearing from Dr. Vivek Dewan, who is a staff scientist at NRAO in Socorro, New Mexico. He provides technical support to both the Very Large Array and the Very Long Baseline Array, and also uses these telescopes to observe radio emission from black holes. Vivek studied physics and electrical engineering in India and in the US before venturing into astronomy. Thank you all so much for being here. All right, so we are now going to have each of our panelists go ahead and take just a couple of minutes to describe their research. So Dr. Kimball, why don't you give us just a short description of what you're doing out in New Mexico?
Hi, everyone. Thanks for having us and thanks for attending today. I'm calling in from Socorro, New Mexico, which is the headquarters of the National Radio Astronomy Observatory's Very Large Array, which is located in about an hour west of here in the desert. So I use the Very Large Array, or the VLA, and other instruments to study quasars, as Amy said. I consider myself both a radio astronomer and a survey astronomer. meaning that I use data in my research that comes from very large surveys of the sky at actually a variety of wavelengths. So I study quasars by comparing data from these different surveys, which could be in infrared or optical or X-ray or radio, to determine their properties and how the properties, their properties in the radio compare to their properties at these other wavelengths. So when I say I'm studying quasars, we'll hear more about that and the various names for these objects. I'm referring to supermassive black holes that exist at the center of basically every large galaxy in the universe, and even some galaxies that are very small. Quasar isn't just a supermassive black hole, it's a supermassive black hole that is active, meaning that it is actually actively growing in size. So there's matter such as gas and dust in the surrounding galaxy that is falling into the black hole and increasing its mass and its size. Some of that matter, instead of falling directly into the black hole, gets directed outward into jets that come out in opposite directions. And those jets emit very strongly in the radio, but they have different properties. And so I'm comparing their properties, such as their morphology, meaning what they look like, and their luminosity and their energy as determined from radio, to how the host galaxy looks in the infrared and in the optical. And infrared and optical can tell us about star forming properties of the host galaxy, what kinds of stars are in the host galaxy. So that's a summary of what I work on.
Well, Amy, thank you so much for that amazing description of the research you're doing right now. And I think everybody, I'm on the edge of my seat personally, and I can't wait to hear you describe more of what you do throughout the rest of the hour. So Justin, that's a pretty tough act to follow, but why don't you tell us a little bit about what you're doing at the Naval Research Laboratory and with Fermi?
I'll see what I can do. So I'm an astrophysicist, yes, at the Naval Research Lab, as you said. And so I work with the Fermi Gamma Ray Space Telescope, which is up in space. It's orbiting the Earth. It's in low Earth orbit. And so, yeah, so the Fermi, it was built with an international collaboration. So it was built with a lot of people from other countries that sort of came together and built different components of it. And so the Naval Research Lab built one of the components of this telescope. And so now, after we built it, we get to use it for science. So for studying and understanding the universe. And yeah, so I study with Fermi, I study things that are very similar to what Amy just discussed. So I study the supermassive black holes in other galaxies. So as she discussed, many of these galaxies, they have jets that kind of go shooting off of them in opposite directions. You know, these jets, they can be pointed every which direction, right? Just by random chance. Just by chance, some of them happen to be pointed directly at us. And in that case, they're extremely bright in gamma rays and in all other wavelengths. And so that's the sort of object that I study. I study the jets of these objects and how in these jets, particles like protons and electrons can be accelerated to nearly the speed of light. And so I study how that process works and try to understand it better. I look forward to talking more about that today.
Great, we're really looking forward to it. As you know, I just came to NRAO from a facility that does gamma ray research. So I'm gonna have a lot of really good questions for you today myself. So finally, Vivek, if you'd like to tell us please how you're studying supermassive black holes and black holes in your own research. Oh, Vivek, you are on mute.
Thank you. I tend to drift between engineering and science. So for my day job, I mostly fix telescopes and help engineering and science staff do their science. For my own interests, I look at black holes at the other end of the size scale. These are black holes within our galaxy. They're about 10 times the mass of our sun. They form when a massive star collapses. And they often eat gas from a neighboring star and spew out jets. It turns out making jets is something black holes do when there are 10 solar masses. They also do it when there are 1 billion solar masses. It's one of the things that scales with the mass of the black hole, and it's one of the ubiquitous processes in nature. It just so happens. So I look at X-ray and radio emission from these objects, which are fairly close by cosmic standards within our galaxy. The nearest one is about 2,000 light years away, something like that. So no, they're not about to come swallow us, but they make copious amounts of X-ray emission and radio jets that come out with it. And we can actually watch this in real time. So one of my colleagues calls this relativity for the impatient, because things that would take millions of years in giant black holes happen in the matter of hours. So we can watch the matter fall in, we can watch the magnetic fields somehow. We don't see the magnetic fields, we see the matter that gets spewed out by the twisted magnetic fields. So it's exciting. It helps to be at a radio telescope like the VLA or the VLBA, where we can jump on an object right away. If we get a notice that something is flaring, you can observe it the same day if you're lucky. So I do a bit of that. Mostly the question of location comes up in my research. Turns out a very long baseline array run by New Mexico, run out of New Mexico, run by National Radio Astronomy Observatory. It has the most precise vision in the radio. So you can locate things to the proverbial gnat's eyelash using this telescope. And that lets you locate the black hole. It can let you measure the distance to the black hole by parallax, which is looking at things from two ends of the Earth orbit. And in some cases, you can even help with other telescopes' data to pin down something as elusive as the spin of the black hole. So this is an object which is invisible and spinning, and we can discuss that later. So the VLBA is a sort of go-to instrument for locating radio emission in the universe, and you can also use it to locate satellites and help NASA pinpoint where their transmitters are. You can use it to locate any object, which if it's bright enough in the radio. So I use that telescope as well, and X-ray emission from satellites. So it's an exciting time, and I look forward to talking to you some more.
Well, great. Thank you so much. That's a really exciting foray into your own research. Of course, you know, I'm pretty new right now to NRAO, and so I'm really excited to hear about all of this research that's going on at our facilities. And I really loved your description, the size of the gnat's eyelash. And I think that gives us all a really good idea of how tiny some of these things can really be, and how small some of these distances can be. But so we've heard a lot of things right now. You guys have said so much. So I want to bring us back to the most basic and fundamental question. And Amy, why don't you go ahead and start us off by telling us your version of what is a black hole?
Okay, so a black hole, okay, well, let me first talk a little bit about gravity. So I think that's a concept that everyone is familiar with because we all live on Earth and we are sort of stuck to the Earth's surface via gravity. But you're able to jump up in the air or throw something up in the air. So you temporarily can fight gravity. And if you were able to throw something like a baseball up in the air fast enough, it would actually be able to escape from Earth's gravity. And that's in fact how we send rockets out into space. They have to reach a specific velocity such that they're able to escape from the surface of the Earth and outside basically the Earth's gravitational realm. So the more massive an object is, the stronger this force of gravity is. So the faster you would have to throw a baseball or send a rocket in order to escape. So a black hole is the concept of a large amount of matter or mass that is squashed into a space that is so small, so it's so dense that the gravitational pull is incredibly strong, so that nothing is able to escape from the gravitational pull of the black hole. So when not even light, which is as far as we know the fastest moving fastest moving anything in the universe, So when even light is not able to escape from the pole, that is when we call that object a black hole. We also define the size of the black hole as the radius or the distance from the center, such that anything, including light, that passes nearby will travel into the center of the black hole rather than being able to escape.
Well, that's really exciting. So we're talking about supermassive black holes in this enormous distance. And Justin, what can you add to what we're now starting to understand about what black holes are as this sort of cosmic abyss?
Well, I don't think I could do a better job than that, but let me describe how you would make a black hole. I thought I would go into that. So if you want to make a black hole, the first thing you'd want to do, if you're under 18, is to get a permission slip from your parents. The next thing you'd want to do is you would want to take a container that is about a spherical container 4 miles in diameter. So that's 4 miles, that's about the size of a small town, right? So you take a container 4 miles in diameter, and into that container, you're going to put, the first thing you would put is all of the people on Earth. So all of the 8 billion people, almost 8 billion people on Earth. There's a lawnmower outside. Can you guys hear me okay? Sorry. Okay, so there's a lawn, somebody's mowing the lawn outside. Yeah, so you put all of the people, then the next thing you do is you put all of the animals on Earth. So all of the dogs and cats and horses and blue whales on Earth into the container. And then you would put all of the buildings on Earth, all of the houses and skyscrapers and the Eiffel Tower and the Empire State Building, put all of that into this 4 mile container, 4 mile diameter container. And then you would take all of the water on the oceans of the Earth. The Earth is 2/3 of it is water. Put all of that inside the container. And then, just put everything else, the entire Earth, inside of this container, 4 miles in diameter. And then do that again 1 million times. So put 1 million Earths inside of this container that is 4 miles in diameter. And then you would have a black hole. So to make a black hole, you need just put a gigantic, huge amount of stuff into this really tiny volume. Yeah, and so the other thing that I just wanted to emphasize is that a black hole, a lot of people think of it as, it's a hole in space. It's some kind of rip or tear in space or something like that. But a black hole, it's really a physical object. It's, it's the thing that's out there like a planet or a sun. And, things can orbit around black holes, and black holes can move around and orbit around other things. And black holes can even spin, and they can do all sorts of things that normal objects in our universe can do.
Well, great, Justin, thank you so much. I mean, that added, I think, a significant amount to what we're starting to really understand about black holes. And I can't believe it, how many Earths would have to fit into a 4 mile wide container to make a black hole. That's it. It's phenomenal. It's kind of mind blowing. And so now we're on to Vivek. And Vivek, I have a very specific need to hear you kind of talk about. So what do we do with that? How do we understand what a black hole is when we start to get this information about it's this space where light cannot escape, and you'd have to have so many Earths to fit inside this small container? How can we really start to understand a black hole for what it means to science and for what it means for us here on Earth? You kind of started to touch on it earlier, and I'd like to hear more about that from you. Yeah,
sure. So my colleagues did a nice job of, painting the background. I'll add a little bit. So the black hole is something, it's a physical entity. It's a strange entity. It's not like ordinary matter. You've crammed all this matter in somehow, and gravity has won over everything around it. So most ordinary objects, if you double the radius of the object, it gets 8 times as massive. The black holes are very strange. If you take 8 times as much mass, a black hole 8 times bigger than another one will have 8 times the radius, which is 8 cubed times the volume. So the volume of the influence around a black hole grows much faster than an ordinary object. So they are strange, if you're far enough away, they look like just a concentrated bit of mass. But if you get close enough, they're not like ordinary objects. So how do we study them? We can't directly see the black hole. There are images recently made of the shadow of a black hole, showing the light not escaping from the center of this fuzzy blob, which we might show you a picture of that later. But what you can study is its influence on the surroundings. The gas that's falling in has to go into a disk, just like Saturn has a disk and all the planets orbit the sun in a disk. It's because of angular momentum, which you can't get rid of easily. So gas falling in makes a disk. The disk somehow twists up magnetic fields and makes these jets. And the jets have influence on the galaxy, which is much larger than the black hole, much larger in size, although it could have the mass not that much bigger than the black hole. So we study the black hole by its effects on the surroundings. And what else can I say? I think I'll stop there.
Well, that's okay, because Vivek, I actually have a follow-up question for you. So as we're talking about black holes, we're talking about them kind of in general, but they're not all the same, right? Just as you've started to allude to here, they're not all exactly the same, and we have different names for classifying black holes, right? So we have a quasar, an active galactic nuclei, blazars. Can you tell us a little bit more about how we classify black holes and what it is that makes them different?
Sure. So one of the things the theorists have told us is that black holes have no hair, something like, some of us are headed that way. No hair in the sense the ones out in the astrophysical domain have no charge. They have nothing, they can't have a magnetic field on them. They can have a mass, which is how they're defined, and they might be spinning. And those are the only characteristics they can have. So just a black hole by itself, all you need to know is its mass and spin. But the way we see them is by the influence on the surroundings. And so depending on how they were discovered, they could be seen, stirring up a galaxy and then be called an active galactic nucleus. They could be beaming a jet right at us, and then somebody would have discovered the jet, which is bright, and called it a blazar. Quasar is a little point-like object with lots of energy, which is not a star. So it's a quasi-stellar object. But it turns out those are the nuclei of galaxies with lots of energy coming off of them. So it's sort of historical. There's a famous black hole in the galaxy Messier 87, which was, some galaxy cataloged by Mr. Messier back in the day. And it was found to have a jet coming out of it and a black hole in the middle. So these are historical names. And you might give the analogy, I'm looking out my window, there's a bird pecking at a tree there. So it's a woodpecker. If I took a photograph, it's black and white and has a red cap on its head. So it's a ladderback woodpecker, and it eats insects. So depending on which type of behavior you describe, or if I just heard it, it would be chirping away and I wouldn't know what it was until I put the information together from many modes of study. And then I could say, okay, this is a black hole with this much gas falling in, this powerful jets coming out, and so on. So these are historical accidents of discovery, but they're useful to describe the black hole.
Great. Well, thank you so much, all of our panelists, for giving us such a really good overview of what really is a black hole. So
Amy,
today,
can I actually add something to?
Yeah.
So Vivek touched on how there are different names for the black hole depending on how they were discovered. So some black holes in how they affect their surrounding galaxy, you see them very strongly with infrared light coming from their near environment, and some don't have very much infrared light, and some have a lot of radio emission, and some actually don't have much radio emission. And some are defined by actually the type of galaxy that they are found in. So there really are a lot of names, and there's a lot of study going on to figure out which black holes that are called by different names are actually similar to each other. Sometimes they're called different names depending on how the jet is oriented, directly toward us or away from us, or sort of at an angle to us. And this is not actually a concept that astronomers have got all straightened out. There was a conference just a couple of years ago that was titled what's in a name. And it was specifically on the topic of all the different names for a black hole and trying to come up with some sort of more organized way of describing them in the literature. And I just thought that it was enough of an issue, and there were enough names that it was worth having a scientific conference with astronomers from all over the world to discuss the topic.
Well, Amy, thank you so much for jumping in to say that, because I think it's so important for everybody to hear that black holes are, even though we've known about them for a long time, they've been cataloged since Messier started cataloging objects in the night sky. You know, we've got 60 plus years of really studying them directly in our more modern time, that we still don't know everything. We don't. And earlier, you guys were touching on the many different ways that we can see how a black hole is actually modifying and having an impact on its own environment, because those particles travel at almost the speed of light, and so you can see that type of electromagnetic radiation across the full spectrum, really making change in many different ways. And so what I think is, today, you know, our presentation is about how to find one, how to find a black hole. And so I think this is a really great segue as we're talking into the different types of descriptors we can use, the different types of names, to really talk about how we're using these telescopes to locate them and to better understand them. So Amy, if you want to go ahead and jump right back in, maybe you could get us started off.
Sure. So the question is, how do we find the black holes?
Yeah, so really, how does your telescope work? And how does it work to find them?
Okay, so well, there are different ways. So as I mentioned, I use the Very Large Array in my research, and I use survey data. So there are surveys of the sky that are taken at, you know, often with dedicated instruments. So there might be a survey that is in the optical, and it uses a telescope that was designed specifically to do a survey of a large region of sky, so that objects are identified without already knowing where they are. And actually, I'm part of an effort going on at the National Radio Astronomy Observatory right now to perform such a survey with the VLA. So because black holes look different at different wavelengths, the different ones are identified in these different surveys. So for the radio, for example, black holes often emit radio, or, you know, the jets that come from the surrounding region of the black hole, that is, emit strongly in radio, and many don't. But there are also other physical phenomena in the universe that emit very strongly in the radio, such as processes of star formation in galaxies. In particular, when massive stars go supernova, there is a radio emission because of energetic particles that are sent out from the supernova, and those actually emit in the radio. So for radio observations, sometimes it's very obvious when there is a black hole, and sometimes it's not obvious whether the radio emission is coming from a black hole or coming from a galaxy that has had a lot of supernova going off. When it is really obvious in the radio is when you can actually see this pair of jets coming out from a galaxy. So jets from supermassive black holes can reach hundreds of thousands of light years, maybe millions. And out into the universe, well beyond the size of a very large galaxy. So if you see two jets coming out from a galaxy, and often they'll interact with the surrounding material and form basically what we call lobes, which are basically you can think of as bubbles of radio emission. You'll see basically a symmetric picture of two bubbles. And that is a really obvious sign of a black hole. You know, that is the only object that has enough energy to actually form those jets. Other times, instead of seeing jets, you'll just see sort of a blob of radio emission. And in that case, it's not clear whether that is actually coming from jets from a black hole. Nick has just shared an image of Hercules A that shows one of these sort of classical pictures of radio jets. So this picture of Hercules A, the radio mission, which was observed with the Very Large Array, is shown in this reddish color, and the background image is an optical picture. So I'll just finish up and pass it on to the other panelists. So sometimes the radio emission is just a blob. And in that case, to determine whether that blob of radio emission is coming from a black hole versus a galaxy with a lot of star formation actually requires using information at other wavelengths, such as optical.
Right, great. So thank you so much, Amy, for that amazing description. And I'm so glad we got that picture lined up. Thank you, Nick, for being able to show us that. So I think this is a really interesting segue, Justin, to be able to talk about why we use gamma ray observatories and telescopes to start looking at black holes in another wavelength. Why are we doing that? What exactly is happening when we point a gamma ray telescope into the sky in a specific direction to understand what's out there? What's going on?
Yeah, well, first of all, let me describe what a gamma ray is in case there are people that aren't familiar with that. So maybe, sure. Nick, could you show slide number 7? Yeah, so you have if you think of light as a wave, right, it has a particular frequency. And so it can go, let's see what we got here. Yeah, so you have, you can think of light as a wave, and it has a particular frequency, right? And so the electromagnetic spectrum, which is just the spectrum of light, goes from radio, so the lowest frequency type of light, all the way through microwave, infrared, visible. Visible is the kind of light that your eyeballs can see, right? Or that you might see looking through a telescope in somebody's backyard. Then you have ultraviolet, X-ray, and gamma rays. And so, you know, as you go to the right on this plot, you go to higher frequency. The wavelength, the waves go to a higher frequency. You can also think of light as a particle. And if you think of light as a particle, you talk about its energy in some unit called, often called electron volts. And so the light that we can see with our eyeballs is, it has an energy of about 1 electron volt, or maybe a little more than that. And the energy that you see so each individual particle of light is called a photon. Each of that has an energy of about 1 electron volt. The type of photons that Fermi sees, the gamma ray photons that Fermi sees, those have energies that are 1 billion times more energetic. So each individual gamma ray that Fermi sees has an energy that is 1 billion times more energetic than the type of light that your eyeball can see. Yeah, so why don't we, let's go to slide, let's go to slide 11. Let's try that. So I was just going to talk a little about how Fermi works real quick, and then I'll talk more about how we can see black holes. So with Fermi, it looks like a giant box with solar panels. And so this is kind of a diagram of the box. So the gamma ray comes into the device, and it turns into it interacts with the material inside of the box and turns into an electron-positron pair. And so that pair is tracked through the box. There are detectors in there that track it. And then the electron-positron pair, a positron is sort of like an electron, but it's the antimatter component of an electron. It has a positive charge rather than a negative charge. They're tracked through the component. And then they get down to the bottom of the box where there's something called a calorimeter, which measures the energy, it measures how fast the electron and positron are going. And so with that information, so this box down at the bottom, this calorimeter is the part that that NRAO builds where I work. So using this, they can reconstruct the energy and the direction of the incoming gamma ray, and they can find out where the gamma ray is coming from and its energy. Why don't we go to slide 9, and we can. I'll talk a little bit.
He's pulling that up, Justin. I have a question for you to kind of help clarify. So when we're talking about gamma rays, when you're observing gamma rays, can you give us a little bit of maybe an analog for what it is you actually see? Right. So with ground-based gamma ray telescopes, of course, we see an ellipse. And so what is it you're seeing in the Fermi telescope when you actually get that data back?
Yeah, you say of course, because everybody knows what a ground-based gamma ray telescope sees.
Of course, they look like a honeycomb.
Why don't we look at slide number 9? I think that will be helpful. This is a picture of Fermi, and so it looks like a box with solar panels here. And so so Fermi is up in space, as you kind of see here, and it's a survey telescope, so it has an extremely wide field of view. So at any one moment, it can see 20% of the sky, and then every 3 hours, so it surveys the sky as it's orbiting, it moves around and looks at the whole sky. So every 3 hours, you can see the entire sky. And so it makes an image a little bit like slide number 9. Okay, so anyway, it makes an image of the entire sky. So what we're going to see in a minute is a map of the sky. Yeah, here we go. So this is a map of the sky in gamma rays. So if you imagine that you have the Earth, you have a globe with Earth, and you can flatten that onto a map. You can project it onto a flat surface, right? I'm sure most people have seen that. So this is something similar, only for the sky, right? You imagine we're here on the Earth, and there's like this sphere around us, and you can take that sphere around us and sort of project it onto a flat surface. So that's what we're doing here. This is the sky, and this is aligned in such a way as the galaxy is this is running horizontally through this. So this red horizontal line here is our galaxy, is the Milky Way seen in gamma rays. And then you can see these little dots here above and below that. Most of those are black holes. So these are, as we've been talking about, these black holes in other galaxies. They often have these jets, and many of those jets are pointed at us just by chance. And so when they're pointed at us, they become really, really bright in gamma rays and at other wavelengths and other energies. So this is sort of what we see with the Fermi telescope. We see a map like this every 3 hours. And we can study gamma rays that way. It turns out these types of objects, these black holes, sometimes they change very rapidly. Like their gamma ray brightness goes up very quickly and then down very quickly. And so the sky can look actually very different from hour to hour or week to week. So it changes very quickly. So when we actually study these black holes, we study how that brightness changes, how it changes very quickly. And then we also study something called a spectrum. So what is a spectrum? So you have photons, gamma ray photons at different energies. You can have them at, say, 1 billion electron volts or 10 billion electron volts. You can make a plot of the number of photons on one axis and then the energy of the photons on another axis, and see how many photons you have at different energies. And you can study that and how that changes with time and things like that.
Great. Well, thank you so much. So I think that's also, I have a million questions for you.
Yeah.
We'll make a good segue. I want to make sure that the public gets the chance to ask you a lot of questions too, and I can see them lighting up to my left. But so Vivek, I'd like for you to sort of jump in here and, feel free to loop back into the radio conversation, but I know you also mentioned observing in the X-ray. And I think that this is a really good time to sort of talk about that difference as well.
Yeah, so it turns out the way hot gas works, it's not strongly beamed, so you can see it at any angle. So it turns out one of the good ways to find black holes is to look at X-ray surveys of the sky, which are done by the Chandra X-ray Observatory, for example, and others. So you see, even in small patches of the sky, you see thousands of little dots of X-rays, which are weaker than gamma rays in energy, but much stronger than, it's the same as your dental pictures are made using X-rays. They go through matter fairly easily. And so they can come to you from large distances. X-rays don't penetrate the atmosphere, luckily enough for us, otherwise we would be mutating much more rapidly. So you have to put those telescopes up in space. Now, when surveys of the X-ray skies are done, you find a lot more black holes than you do in the radio or in the gamma rays. And the reason is that it's easy for hot gas to make X-rays. And they're not strongly beamed, so you can see them at any angle. So there's more of them, apparently more of them out there. And so we know that many, many galaxies, in fact, most reasonable sized galaxies have a black hole in the middle, depending on how much gas it's being fed or grabbing from its surroundings. It may be brighter or dimmer, and a fraction, maybe 10 or 20% of those make radio jets. So the best way to find a black hole is to search in the X-rays and look at that swirling cloud of gas that's going around the black hole prior to falling in. Of course, the jets are a great signpost as well. So you look for the signposts, and the black hole is right in the middle. And I would like to show the slide with the like the third to last with the VLA sky survey. The image with lots of jets on it.
While they're pulling that up, Vivek, do you mind telling us why are hot gases easier to see in the X-ray than in other wavelengths?
Oh, it's like the sun is at 5,000 degrees and our eyes evolved to see that. And the wavelength is half a micron if you measure things in microns. X-rays are from million or billion degree gas around the black hole. As the gas falls in, it heats up from friction and it emits primarily in the X-rays, just as the sun emits primarily in visual light. And so it's a great signpost for where the black hole is stirring up the gas. And if you look in the radio, this great image, which I hope Amy will discuss right after me, every little dot in the middle of each of these little panels is the location of the black hole seen in the radio. And the two blobs on either side are the radio emitting jets. Amy will tell us how we find these, but so these are the signposts of black holes, which are almost certainly emitting in the X-ray, although I don't have an overlapping X-ray image to show you. So these are almost guaranteed to be emitting in the X-ray, and a fraction of those, 20% or so, emit radio. And so this is what you see. This is how you locate a black hole. You can zoom in on it with a telescope with better angular resolution. And you can also look for gamma rays and X-rays and optical light and infrared, and put all that together to give you a better picture of what's going on. Okay, so.
All right, great. Thank you so much. So I think, Amy, if you have anything you'd like to add to what Vivek was just talking about with VLAS, or if you'd actually like to come in and also talk to us a little bit about how telescopes collect light, because I want to make sure everyone in the audience out here has a good understanding of how that process is happening, I think that would be great.
Sure. So do we have a, yes, Nick, could you show slide? Yes, perfect. You read my mind. So here's a picture of the Carl G. Jansky Very Large Array Radio Telescope in New Mexico. So this is an instrument that we use to observe the sky and the radio. Justin earlier described when he was talking about gamma rays versus light rays at other wavelengths, other energies, that light can act either like a wave or like a particle. And that's a very interesting and confusing quantum mechanical issue. But depending on the energy of light, we observe that it has properties more like a wave or more like a particle. It happens that in the radio, where energy of light an individual ray of light is very low relative to, say, visible light or X-ray light. In radio, light has many more particles many more behaviors like a wave. So it behaves like a wave as it's traveling through space. So each of these antennas that is part of the Very Large Array Telescope, we're seeing a picture of them right now, is basically has a parabolic dish. And what happens is that light comes in from the distant universe and reflects off of that dish, and then is directed up to the location where you can see. Let's see. So the big telescope, the big antenna in the forefront, just on the left of this, you can see that in the center there's a structure there. So light comes in and bounces off the main dish, and then is focused by that reflection up to the top of that structure, and then is directed into a receiver where the light is actually then where it's actually detected, and then it's digitized so that we can record digitally how much light came in at different frequencies and at what times and so forth. so the size of the main dish here actually is a clue as to the energy and wavelength of the light that is being detected. So radio waves have very long wavelengths and require very large dishes in order for us to be able to detect them. And the neat feature about the VLA is that it's actually 27 of these individual dishes observing at any given time, and they can actually be spread out across the desert, or so that they're in a very large, they're extended a very large distance from each other, or they can be condensed so that they're a very close distance from each other. By having these 27 individual dishes, what radio astronomers can actually do is basically act as if there was one giant dish in the desert that was the size of whatever the separation of the dishes is. So if we want to have a dish that observed the sky that had a diameter of, say, 30 miles, that would take a lot of metal and a lot of construction. It would be very difficult to make a dish that was 30 miles across. So instead, we make individual dishes that are much smaller, and we spread them out a distance of 30 miles. And in doing so, they actually sort of act as if they were that very large dish. I could say a lot more about other things and about the survey. I don't want to.
I know. Thank you so much, Amy. Vivek and Justin, do you guys have anything you'd like to add to this part of the discussion? Feel free to unmute if you do.
I think she pretty much covered how radio telescopes work for now.
Okay, so well, thank you guys so much. And Vivek, did you have something to add? It looks like you're on mute there. Okay, just want to make sure. So we have actually, you guys, a ton of really good questions in our chat. And so we're actually going to move on now to the public questions. So it looks like our first question up here today is from an anonymous attendee. We have, why do particles accelerate away from a black hole if gravity is pulling them towards the black hole? Who's up for that one?
I guess it's my turn. So
thanks for being brave, Justin.
Yeah, why don't we start with, can we look at slide 12? Yeah, so you have a black hole, right, as we've been talking about, and you have all of this matter that's kind of falling onto the black hole. So when it falls on it, it starts out with some sort of angular momentum, so it starts going around the black hole. And in the this stuff that's falling onto the black hole, it's a plasma, so it has the atomic nuclei and the electrons are sort of separated from each other. It's like a gas where the nuclei and the electrons are sort of separated from each other. So you have all of these charges that are moving around. And the charges can make magnetic fields as they're moving around at these very high speeds. And then you have the black hole, which is spinning very rapidly. And so when you have a black hole that's spinning rapidly, it can sort of drag around. It can actually drag around the space around it. So these magnetic field lines around the black hole, they get sort of spun up as they're going around the black hole. And you can sort of see, this is an artist's picture. This is not like a picture that astronomers took with the telescope. But you can see some lines here in the blue. You can see, so these are supposed to represent magnetic field lines. So you can imagine the magnetic fields are getting spun up as the black hole is spinning, and the matter kind of follows those magnetic field lines and gets accelerated into this jet that's moving out. And so, so then this jet would then connect with all the pictures that we've seen before, all of these pictures of these giant jets that are 100,000 to 1 million light years in size.
Well, Justin, while you're still here, let's explore another question that's pretty tied to to the size and distance issues and the way that black holes really impact galaxies. So we have a question here in the chat. What came first, the black hole or the galaxy?
Oh yeah, that's a really good question. So the answer is that's an active area of research, which is what scientists say when they don't know the answer. That's something we're still working on. So we're not, it's not totally clear which came first, the black hole or the galaxy, but what seems likely is that they evolved together. So the supermassive black hole at the center of a galaxy and the galaxy around it, there are a lot of clues that they sort of evolved together. And some of that evidence is that if you measure the speed of the stars going around in the galaxy, they're well correlated with the mass of the black hole. So there are some strong indications from clues like that the black hole and the galaxy, they sort of co-evolved together, but I don't think it's totally clear exactly how this process happened.
And I just telling you, I'm going in order here, so you're not off the hook just yet. We now have two questions. I'm actually going to read them for you together because they're both very specific about the Fermi telescope. And don't worry, Amy and Vivek, I have questions for you too. And I am bringing you back, so don't go anywhere. But Justin, why is the Fermi telescope space-based? And then can you also tag on to that and tell us, does Fermi produce astronomical images like the Very Large Array?
Yeah, so it's in space. I think that Vivek said this, but he said it very quickly. The telescope is in space because the gamma rays don't go through our atmosphere. So the radio waves and the eyeball light, the light that our eyeballs can see, it does go through the atmosphere, but gamma rays do not. So we have to put it in space in order to see things with gamma rays. And then the question was, does it make images like VLA? That was the other question, right? So yeah, so the answer is no. And why not? So with things like radio waves and with eyeball light, like your eyeballs can see, you can focus that light with mirrors or lenses in the case of optical light, or with radio dishes in the case of radio waves. But with gamma ray astronomy, you can't focus the light in the same way. So it's a very different type of technology to what radio waves and optical telescopes use. Gamma ray astronomers are very unfocused, and so are gamma rays. Yeah, and so the resolution that Fermi has is it's very poor. It's actually it's about the size. If you imagine resolution like the resolution of a camera or the resolution of a television screen or something like that, and you imagine it in terms of pixel size, each pixel that Fermi has is about the size of the moon. So it's really gigantic. Whereas, yeah, I don't even know how maybe Amy or Vivek can say what the resolution of VLA is, but it's very, very good.
Yeah, sure. Amy and Vivek, are you out there? Do you know what the resolution is on the VLA? Well, I know you know. Can you share with our audience?
Sure. So the answer actually depends. It depends on two features. One is the specific radio frequency of light that is being observed for a particular observation, and the other one is how far spread out the dishes are. So as I mentioned, the VLA 27 dishes can be spread out. They can actually spread out to a separation of about 30 miles, and they can be as close together so that all 27 dishes are within about 1 kilometer. So this picture that Nick has just shared of the VLA is in the most compact configuration, and it's actually the most photogenic because you have all 27 of the dishes very close together. So when the dishes are very far apart, that is when they get the highest resolution, so the best resolution on the sky. And when they are close together, that is when they actually get worse resolution, but overall there's a better sensitivity to light. And so I'd actually ask that Nick, if you could show slide 15. So this is Hercules A viewed in 4 different configurations with the Very Large Array. Thanks, perfect. So the VLA has 4 standard configurations, which we creatively labeled A, B, C, and D. And this is the different images of Hercules A as it was observed in each of the 4 different configurations of the VLA. So A, which is shown on top here, is the configuration when the antennas are spread across the desert the most. So there's a separation as large as about 30 miles between any between a pair of dishes. And so this actually, you can see when it has the best resolution, so you see the finest features. But actually, if you look then down at the bottom in the D configuration, we can actually see more emission on a larger scale. So actually, it's very important sometimes to observe objects in the different configurations with the VLA, so that you can actually put together the most information about what the radio emission looks like. So if I were to describe the actual resolution, wow, I know what it is in units that astronomers use, but I don't know if I have a good analogy for it. And so I'm going to ask Vivek if you want to.
How good is it compared to what the eye can see? How much better is it than the resolution of the eye? So that resolution of the eye, let's say, is 1 milliarc second.
1 million. Oh, Vivek, I'm gonna pass it to you.
Okay, sure. So our eyes see about an arc minute. The VLA goes between arc minutes and arc seconds, and somewhat less if you use a short enough wavelength and separate the antennas out. And the VLBA, which is the other prosaically named very long baseline array, can coordinate signals from antennas which are spread across the globe, which is, so the separation of the antennas can be 10,000 kilometers, which lets you zoom in on those little dots that you saw in the previous picture. And that gives you a resolution of 1,000th of an arc second. So 60,000 times improved from your eye, which needs bright objects to emit a lot of emission in that small region. So we are looking at the brightest jets from black holes beamed at us. And you can make movies of those and you see interesting effects there. So the resolution is the key to radio because it lets you match up the central region of a galaxy. You know exactly where that black hole is. You can measure how fast it's moving in a few weeks for the ones within our galaxy. For the distant galaxies, they move much slower. So radio is the key to locating and tracking these things, but we need the other wavelengths to, of course, make a full picture of it.
Great, Vivek, thank you so much. You guys, we are just about out of time. This hour has just blown by. We have one really interesting question out here that I want to give everyone just about 10 to 15 seconds apiece to answer. So Vivek, don't go anywhere. So we're going to have you go first. It is, what happens to time near a black hole? And what would happen if someone fell into a black hole?
Oh, what happens to time, I might be able to answer, though I'm not a theorist. They tell us that time stretches out near a black hole. So things go slower if you, in my frame, if I watch you fall into a black hole, you may not feel any change. Your life will go on as before, but I would see you stretched out physically by tidal effects and stretched out in time. And your scream would be red shifted. So your scream would be lower pitched than the emitting sound that you made. What do you feel? I don't know. I think there are good answers. There's a Black Hole 101 in the National Geographic website. Take a look.
I love it. I love it so much. Amy and Justin, you guys are out there. Do you have any last thoughts about time, what happens to time and what happens to people if we go into a black hole?
Yeah, I don't have a lot to add. Yeah, just as I guess repeat what Vivek said. Yeah, as you go into a black hole, yeah, time will do very weird things. So as you're going into a black hole, you know, as you get closer to the black hole, maybe there's a link there in the chat about to the National Geographic article. As you go into the black hole, maybe like 1 hour for you would be like 5 years to somebody on the outside or something like that. It's actually, there's also the movie Interstellar where this sort of thing happens, but time would run very differently for you as you get closer to the black hole. So if somebody from outside was looking at you as you were going to the black hole, they would see you going really slowly. Time would be very slow. And then you would be looking at other people outside the black hole, and you'd be seeing your friends in a spaceship that are far away from the black hole. They would be moving really, really fast they would appear as in fast forward to you.
Wow, I mean, like that's so we get to see the world in hyperspeed, basically, and we're all going to become baritones. That's what I'm hearing from you guys.
I'd like to just add one other thing, Amy, which is, so Vivek mentioned that you would get stretched out because of tidal forces. Basically what that means is that as you get closer to the black hole, say you were falling in feet first, your feet are closer to the black hole than your head is. And so the gravitational pull on your feet is actually stronger than the gravitational pull on your head. And that difference in gravitational forces near a black hole is so strong that it actually will overcome basically the molecular forces that hold the atoms in your body together. So you would actually really would be stretched out because gravity is pulling your feet so much stronger than it's pulling your head. And so we actually, astronomers have a fun term for that, which is called spaghettification. So you would be spaghettified if you were to fall into a black hole. Of course, how much it happens is actually a matter for the theorists to tell us.
So we're also all going to get a little bit taller. I could use a few extra inches. I accept. So, well, Amy, thank you so much. Justin, thank you so much. Vivek, thank you so much, all of you, for your amazing answers today and everything you've taught us about the basics of black holes, what happens if you fell into one, and how to find one. So we are wrapping up here. Thank you to our great audience for all of your amazing questions. We're still answering questions in the chat, but now I'm going to hand it back over to Nan. She has just a few things she wants to tell you about, and then we'll see y'all soon.
Thanks, Amy.
Hey, thanks everyone. This was great. We just have one. Hey, Nick, can you bring up the slide for the CDL? We just have one announcement to make about our Central Development Laboratory, which is in Charlottesville, Virginia. And we have a virtual tour on April 24th from 1 to 2 p.m. Mountain Time. And this is basically an overview of the operation and evolution of NRAO's multiple radio telescopes. It would not be possible without the technology that's being developed at the Central Development Laboratory. And we'll have some guest experts, Denise Almeida, a mechanical engineer, and Jennifer Jackson, a technical expert, a technical specialist. So join us on Saturday, April 24th from 1 to 2 p.m. MDT, and you'll be able to sign up. I'll put the registration link in the chat. And you can also go to NRAO's public webpage and sign up for the event then. Just a welcome, a very heartfelt thanks to all of our panelists and to our amazing moderator, Amy Oliver. Thank you all so much for joining us today for Black Hole Week. Okay, see ya, everyone. Bye.
Thank you. Bye-bye.